potential. Okay, like potential. And then there's the one form, E and H field.
What do these mean?
Huh?
What do 0 form, 1 form?
I'll try to tell you what they mean in a little while. Okay, let me just classify them at this point. Two forms, B and B. Three forms, tau. These are fluxes. Tau. Okay? And zero forms are things that are associated with scalar quantities. Okay? Yes, things that are associated with scalar quantities, and they are functions of space that you can take gradients of. They are only associated with one point in space. So this is associated with points. And then the E and H fields are associated with lines. But E lives on the line. H also lives on the line. Okay, lines. And then fluxes are quantities that live on surfaces, like they go through surfaces. Okay, so these fluxes are associated with area. And then the densities are associated with volume. Okay? So, what you can show in electromagnetic theory is that the gradient of potential gives you the one form. And then the curl of the one form gives you the two forms in electromagnetic theory. Curl of E gives you the VDT, curl of H gives you the DDT, and so on. And then the divergence gives you the three forms. Okay, this is how things go in electromagnetic theory. Okay, and then it turns out that in this differential form calculus, in differential geometry, all of this can be written with just one operator. Okay, all of this can be written in just one operator. So you will have df. I think this is called the exterior derivative. df is equal to something. So all the gradient, the curl, and the divergence operator can be written as one. If you define this quantity properly, you only need to have one derivative operator called the exterior derivative. And depending on what f is, if f is a zero form, this exterior derivative miraculously becomes a gradient operator. If this f is a one form, this exterior derivative becomes miraculously a curl operator. And then if this is a two forms, it becomes a divergence operator and so on. So it's like in this object-oriented programming, right? This is like an overloaded operator. One operator, it gives you different results. So this is a wonderful operator. But there's only one mathematical definition of what this exterior derivative is. Okay, you can define it and write it down mathematically in differential geometry. And then you can also write this zero form, one form, two forms as different quantities in differential geometries. Okay. So what I feel why E algorithm is so robust is because E algorithm actually adheres to the rules of differential forms. That it let the E and H field live on edges. Okay, E and H field lives on edges. And then E and H also lives on interlocking edges. Okay? And then when you have the fluxes can be associated with the areas, the cross-sectional area of these spaces. So E algorithm tries to adhere to differential geometry and the differential forms of electromagnetic theory as much as possible. That's why it's so stable. Okay? Another thing that for those who do computational electromagnetics, you might also find that these forms actually are forcing you to do different things in computational electromagnetics. Like, you will notice that if a quantity belongs to the zero form, you can only approximate them with nodal elements. If something belongs to the one form, you can only approximate them with the H elements. H elements like, what do we call it? Another basis and that kind of thing. Okay? If something actually belongs to the two forms, you can show that you can actually take the curve of the one form to become like a two form, those bases that you work with. And so on and so forth. Okay? And if your computational electromagnetic algorithm do not abide by these rules, usually they don't produce good results. That's what I find. Okay? So there's some intimate relationship between the forms and how you do computational electromagnetics. And there is a lot of talk on how to find bases for E and H. And those bases are called the H elements. They are curve-conforming bases. So things that live in the one-form world, they have to be curve-conforming. And then there will be things like B and D and J actually. And those things that belong to the two forms, they have to be expanded with bases that are called divergence conforming, because it's the divergence of these quantities that exist. It's the curves of these quantities that exist. Okay, and then the charge, I guess, I'm not quite clear about that. Maybe you can still use nodal elements for those. Okay, so there is an intimate relationship between differential geometry, computational electromagnetics, and also the finite difference time domain algorithm and the E algorithm. E algorithm can be easily converted to a finite difference frequency domain algorithm. You can cast this. But if you take away this, this becomes an eigenvalue problem. And you can solve this problem in the cavity. You can solve this problem in the cavity, and this becomes the eigenvalue problem for you to find the resonant frequencies of arbitrary shaped cavity, for instance, if you have a very complicated geometry. And it can be very complicated shape too, as long as it can fit into this E grid. Okay, very complicated geometry. You can solve this equation with the proper boundary condition. You have to apply boundary conditions to these x values near the boundary. And then you can solve that as a eigenvalue problem, or generalized eigenvalue problem. MATLAB has a lot of programs for you to find eigenvalues of this. You'll find that this will give you the resonant frequencies of the cavity with no spurious mode solution. No spurious solutions, unlike finite element. Finite element, if you don't do it carefully, you end up with spurious solutions, not charge conserving and so on. Okay? So are there any questions regarding this? I guess I can send you this paper and you can read about the rest of the things, proof of reciprocity theorem, discrete pointing theorem, and all the things that are in there, discrete Green's theorem and so on. Okay? You can read about that. I'll send you this paper. I guess I won't start on a new topic since I only have 1 minute left. The optional problem is optional. Actually, I can say you can give me a simplified answer. Just tell me the physics of the branch point contribution. You don't have to derive the details. Details are too hard to derive. And to do a lot of work to derive the branch cut contribution.